Hello everyone, beginning the 14.6 video here. So 14.6 is about directional derivatives and the gradient. So let's first discuss what that even is, okay? Directional derivatives, that is. So recall for these multivariable functions, for a lot of our operations, we're concerned with direction, right? Limits, continuity, derivatives. And for the derivatives, we've been confining ourselves to the directions of our major axes, right? The x-axis and the y-axis, meaning we've been looking at the derivatives with respect to x and respect to y, these partial derivatives, we call them, right? So what do those look like? Okay, so maybe this blue surface is the graph of my function, and I have these yellow tangent lines, right? So what does this one represent? Okay, so maybe that's the tangent line. Okay, so maybe our point. Okay, so we have this point in our domain in the xy plane, and then this yellow point is up, or this point up here is its functional value. Okay, so maybe the derivative, like if I move in the x direction, right? So this is the x-axis. So maybe if I'm looking along this line parallel to the x-axis, I take the limit, I get my derivative, which gives me the slope of this tangent line, right? So partial derivative with respect to x gives me the slope of the tangent line if I'm looking at a line parallel to the x-axis. And then the partial derivative with respect to y, f sub y, that gives me a similar thing for tangent lines kind of parallel to the y-axis, right? Okay, so maybe I'm considering inputs, along this line in my domain, okay, and I take the limit of my fraction, right, f x y plus t minus f of x y over t. I take that limit, that gives me a number, and that's going to be the slope of this tangent line here, right? All right. So that's what that's what our partial derivatives are. But really, I can do this sort of operation in any direction, right? There's no reason I should be confining myself to just the x and the y axis. Maybe I want to take the derivative in some other direction. Okay. So I have this point in my domain that's mapping to this point up on my graph, right? So maybe instead of looking for derivatives in the x direction or the y direction, maybe I want to look for derivatives in some other direction. What about this direction here? So what if if my inputs, what if I'm looking at the inputs along this line, right? That if I take the limit of, if I kind of construct a similar thing, f of x plus something minus f of x over that something, that should give me the slope of some tangent line kind of in that direction, right? Okay, so it's a derivative in this direction. Okay, so we would like to be able to do that. We don't really have a machine. We don't really have the machinery to do that right now, right? We just constructed our partial derivatives along the major axes, like with respect to x, respect to y, z, and so on. So we need to build up this machinery. So this is just, all this text is just kind of restating what I said. What if we want to find a derivative in the direction u? Okay, so we said we are looking at derivatives. Now, when our inputs are along maybe this vector instead of along the x-axis or pointing in the direction of the x-axis or y-axis. So what is this vector? This could be some arbitrary vector u. Okay, that's giving us our direction. Okay, so we want to find our derivatives in some arbitrary direction u. The problem is, we have a function of fx and y. For the derivatives with respect to x, if I had like fxy equals, x squared y plus y, or maybe xy cubed. If I want to find the derivative in the x direction, that's really easy. I have this kind of shortcut, right? I differentiate with respect to x and I leave y constant, right? But if I want to differentiate with respect to u, this vector u in this direction u, that's a little more complicated because, how do I do that? How do I attack this equation to get my derivative with respect to u? There's no u's in here, so I can't just differentiate with respect to u, right? So, we're kind of missing something. All right, so let's start developing this theory. How do we differentiate our function in some arbitrary direction? Okay, so we're going to start by assuming f is a multivariable function from Rn to R. Okay, now I'm going to go ahead and start from the beginning where I'm kind of working in this general multivariable case. I'm not going to, we'll consider R2 to R as a special case, but let's keep it general for now. Okay, so let's assume f is a multivariable function Rn to R. Now I could write it like this, right, where I have f of x1, x2, etc., all the way to xn. But that can get cumbersome after a while. So a way we abbreviate that, instead of writing x1 to xn, I'm just going to write f of x, f of the vector x, okay, where x, the vector x, is equal to what? X1, x2, and so on. So they mean the same thing. Okay. Now we want to find the derivative of f in some arbitrary direction u, of this vector u, and really u is just telling us a direction, right? Its magnitude doesn't, it's not really factoring into what we're doing. So to keep everything simple, we'll just say that whenever we're finding a derivative in some direction of a vector, that vector is going to be a unit vector. Okay. So let's just assume that this vector u is a unit vector, so it has length 1. Okay. Now, just like with other derivatives, we're going to define this thing. We're going to define our object, this directional derivative. We're going to define it as a limit. And what is the limit going to be? Okay, we're going to set it up like this. So this should look very similar to what you saw in Calc 1 for the definition of a derivative, and what we've seen in Calc 2 and Calc 3 so far. It's just this limit of this fraction here. Okay. All right. So this notation means the directional derivative. We call it a directional derivative because we're talking about a derivative in a specific direction. We call it the directional derivative of f with respect to u, or we can think about it as the derivative of f in the direction of the vector u. Okay, so this is our notation now, and we're going to define it as this limit. Okay, the limit of h, the limit as h approaches 0, where h is just some number. Okay, some real number. And what is the limit? It's going to be the limit of f of this vector x plus h times the vector u. Okay, so this is a scalar, and we're multiplying it by this direction vector u. Okay, and then we're subtracting our f of x, and then we're dividing by h. So it's very similar to our previous definitions of derivatives. And we can think about it as, rise. We can still think of it in some sense as rise over run. And we're taking that limit as this h goes to 0. So we could, before we go on to, well, we can go ahead and consider, we can be specific. So when we're talking about a function from R2 to R, and I'll draw kind of a picture of what's going on in a moment. Let's kind of narrow down this definition to the specific case of the function from R2 to R. So let's say f of our function f, let's just go ahead and write it as f of xy. When there's only two components, we could write it like this, but we don't save that much time. So let's go ahead and just leave it like f of xy for now. Okay, and let's say our vector u has these components a and components b. So it moves a units in the x direction, b units in the y direction. And then let's just rewrite this for R2. Okay. Well, I'm just going to rewrite my limit, but I'm just going to do it in the special case of R2. Okay. So this f of our vector x plus h times our vector u, well, I could just write that like this, right? H times my vector u is what? Since my vector u is equal to this, h times u is just a times h times a times, or h times a comma h times b, right? So f of the vector h plus h times the vector u becomes this thing, okay? With that in mind, we can rewrite this as this. Okay, so take a moment, pause if you need to look at this. So when we're talking in R2, we could use this if it makes it a bit clearer what's going on. Okay, these are the exact same thing. Okay, so now let's take a moment. I'll draw kind of a quick picture about what's going on graphically. Okay, so again, we're considering the limit of, let's keep it with the R2 case. Okay. So let's say I'm at some point x, y in my domain, right? And then my function, it's got some graph. And then I graph my function value of fxy. Maybe it's up here. Okay. And let's say this is just, it kind of appears I've just drawn a flat thing. Let's give this some structure to it a little bit. So let's say it's kind of this hill type thing. Okay. So this is the point, what, x, y, comma, f, x of y. Okay. All right. So what would f of x, what would this point be? Okay. What would f of x plus ha, y plus hb be? So let's say this is the point x plus ha, x plus, or y plus hb. And again, this is in my domain, right? In this kind of horizontal xy plane. Okay. And then I plug that point into my function, maybe I get this point. Okay. So this numerator here is the difference between these function values. Okay. So it's the vertical, in this case, it's like this vertical distance here. Right. So let's say there's some vertical difference between these two. Okay. So that would be this distance is my numerator, my f x plus ha, y plus hb minus fxy, right? And then what's my h? let's see, I'm moving h units in this direction, h units in this direction. Well, that's not quite true. I'm moving in the direction of my vector u, right? Okay, so my vector u is the vector with the components a, b. Okay, then I'm multiplying that vector by h to get h a, h b. Okay, so really I'm moving h a units in the no, h a units in the x direction. Remember, this is my x axis, y axis. Moving HB units in the y direction. And then what is the length of this side? Well, it's going to be, we could do Pythagorean theorem and all that. The length of that side there, the length of the vector we're actually moving along. Okay. Well, really, forget about, Pythagorean theorem in a second. It would be h times AB, right? And remember, our vector u is a unit vector. It's got length 1, okay? And by the properties of our vectors, we know that this length is the same as absolute value of h times the magnitude of that vector AB. And remember, this vector is a unit vector. It's got length 1. So the length of that side is just h. So what's going on in this fraction? We said, okay, this difference here in the numerator, that is our change in elevation, our kind of rise, if you want to say. And then our h is our run, right? It's our change in this kind of horizontal distance. So again, we still have rise over run. So this derivative is still giving, this limit should still be giving us our slope of the line. Okay? The slope of the line between these 2 points. And the idea is, okay, I'm taking my limit as h goes to 0. As h goes to 0, these points are getting closer and closer to my original point, xy. And my line is changing, and it's getting closer and closer to the slope of the tangent line at that point, xy. So still very similar to our previous ideas of the derivative. Let's see, where was I? Probably here. Yeah. Okay. So that's the idea. That's the definition of what the directional derivative is, but it doesn't really tell us how to calculate this, right? It would be cumbersome, as I say here, if every time we wanted to find that directional derivative, we had to compute a limit. Just like with regular derivatives, we have a very similar for the definition for the definition for a derivative in the single variable case, but that limit is not actually how we compute the derivatives, right? We have all these nice rules and shortcuts to compute derivatives. So we would like something like that for the directional derivative. Okay, just like we have for finding the partial derivatives or derivatives for functions of single variables. And we can find this shortcut kind of inside our theorem from our previous section 14.5. So let's say our function f, our multivariable function, is differentiable. Okay, so remember what that means. Okay, it means we have this linear approximation, right? Where I can write delta f, which is just, this is delta f, right? Our difference in f, okay? Between if I'm considering a starting point xy, and then I'm adding the vector h a b, okay? Okay. What's the difference between f of this and f of xy? That's our delta x. which I've rewritten here. Well, from the definition of a differentiable function, differentiable multivariable function, we know we have this linear approximation, which is going to be given by this, right? It's going to be given by the partial derivative of f with respect to x. Okay. So f sub x times the x component of, this change, hi, plus the partial f sub y times hb. And then we have these error terms here, plus epsilon 1 times ha, epsilon 2 times hb, where the limit of epsilon 1, well, that goes to 0 as h goes to 0, right? And so does epsilon 2. Okay. So this is just our delta f. Okay. And where are we going with this? Well, our derivative should be the limit of delta f over delta h, right? So that's kind of where we're headed. What is delta f over delta h? This is our delta f up here. Okay. And then what's our, if we divide by delta h, what's going to happen? Well, let's see. These h's here, 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 and here are going to cancel out if I'm dividing by delta h, right? Or this should be delta h, this should be just h. Okay. So if I divide by h, my h's should cancel out, and I should be left with this, right? And now let's take the limit of this as h goes to 0, okay? And we're going to call that thing the directional derivative, or that's the definition of our directional derivative, all right? And as long as f is differentiable, okay, it's going to be equal to this thing, right? Let's take the limit of all this stuff up here. Limit of h goes to 0 of all this. Okay, well, this is essentially just a constant, right? I don't have any h's here. I don't have any h's here. Okay, so nothing's going to be changing about these as h goes to 0. And then remember, by our definition of differentiable, this epsilon 1, well, we know limit of epsilon 1 h goes to 0 is equal to 0. So the limit of this term is 0, and the limit of this term is 0. I'm multiplying by these numbers a and b, but it doesn't matter what those are. If epsilon 1 and epsilon 2 go to 0, well, then these both go to 0. Okay. So when I take the limit, these terms disappear, and I'm just left with these. So it turns out our directional derivative, let's say I have a function f, xy, okay, at the point xy, and I want to find the derivative in the direction AB. Okay. Well, it turns out that derivative in that direction, if this is differentiable and this is a unit vector, that derivative is just going to be given by this: f sub x times a plus f sub y times b. Okay. So this is our shortcut. This is how we evaluate that directional derivative. Okay. So let's see it in action here. So let's say this is my f of xy, and I want to find the derivative of f in this direction. Okay, so this is a unit vector. This u is its magnitude is 1. If I find the length of this vector, its length is 1. So I want to find the derivative of f in this direction. Okay. Well, we know by our formula right up here, okay, it's going to be f sub x times the first component, the a, so 1 over 2. And then it's going to be f sub y times the second component, square root of 3 over 2. So I got a lot going on my screen. I apologize. Okay. So du f xy is going to be, well, I need to find my partial derivatives, right? Okay, so let's find f sub x. Well, what's f sub x? It looks like it's going to be exy plus 3y squared x squared, right? And then what's f sub y? Well, that looks like it's going to be ex plus 2y x cubed, okay? So my directional derivative in the direction u should be exy plus 3y squared x squared times a, okay, which in this case is 1/2, plus ex plus 2y x cubed times b, which is square root of 3 over 2. All right. So that's my directional derivative in the direction u, okay? And in particular, if I was further told, this is still kind of general. We don't, this is just for a general point xy. Let's say I was told specifically I want to find du f xy at the point, about 0, 2. Okay. Well, then I have my general expression here. I just plug 0 in for x, 2 in for y. Okay, so what's the directional derivative of f at this point here, 0, 2? Well, I plug 0 in for x. I get e to the x, e to the 0 is 1. Okay, y is 2. Okay, plus 0 times 1/2 plus 1 plus 0 times square root of 3 over 2 equals 1 plus square root of 3 over 2 equals this. Okay, so what does that mean? It means at this point 0, 2, right? I'm just going to draw a quick and completely inaccurate probably sketch of my function. Let's say my function looks like this. And I always draw them with like a hill, just so we can see some elevation. And then let's see, let's do a bit better. And then let's say this is the point 1, 2. So at this point, I look at my functional value, right? At this point 1, 2, I trace it up to the surface to get its like functional value. At this point, it's got a tangent curve. It's got a bunch of tangent lines, right? Pointing in an infinite number of directions. But I'm considering the tangent line that's along the curve, along the tangent, along the vector u 1/2 square square root of 3 over 2. Okay, so what direction is that? That would be pointing in what, like somewhere in this direction, right? Okay, so let's unclutter this a little bit. Okay, so in this direction, okay, there is a tangent line kind of along that direction, right? And it might be kind of level, might be like horizontal, or it might be kind of slanted. It's kind of hard to draw, 3D slope on an iPad or on any kind of flat surface. But think of it as moving along this line, but it could be sloped up or it could be sloped down, right? Well, this number here is the slope of that tangent line in that direction. Okay, so let's see. In this direction, our slope is positive, so it looks like this line here, this tangent line along that direction is kind of sloped up. Okay, so we could kind of think of it like, again, it's kind of hard to draw. Okay, so again, kind of picture this moving along this direction, but it's sloped upward. All right. So that's how we compute this. But again, there's even a more efficient way to think about this. Kind of a cleaner way to write this. Okay, this is kind of, maybe it's a bit to memorize. Okay, so there's kind of a nice compact form that it kind of helps us compute these directional derivatives. So let's play with the notation a little bit. Okay, so let's focus on these partial derivatives here. Okay, and let's make a vector out of them. Okay, so where I'm going to put the f sub x in my x component and the f sub y in my y component. Okay, I'm making this into a vector. This vector is, it's a special vector. It's got a special name. We call it the gradient vector, or just the gradient. And we denote it by this upside down delta f. Okay. And we would pronounce that del f. Okay. So this is a vector. So I'll usually kind of leave off the vector arrow. It's just kind of well known that this is a vector. So we usually skip the vector sign over it. But when you see this, you should think, okay, it's the vector whose components are the partial derivatives. Okay. Now let's look at this term up here. Okay. So this is remember this is the first component of my vector. So this is like the x component of this del f, and this is like the y component of del f, right? And then, okay, I have these a's and b, this a and b here. So how can I think about that sum? Well, that's a dot product, right? So I've rewritten my sum here, okay? If this is the x component of my del f, and this is the y component, well, I can think of that sum as the dot product of the vector del f with the vector u, right? Because remember, u is the vector a, b. Okay. And, if you want to kind of reassure yourself of this, write it out. What is del f? Del f is equal to f sub x, f sub y, all right? And then I'm doing the dot product with u. Okay, so let's just kind of keep track of everything. All right. Well, what is that? That would be fx times a plus fyb. And that's exactly what I have here. Okay, clean that up. All right. So this gives a nice compact notation for my directional derivative, right? So I have du fxy in the direction of u. Okay. This sub u here is telling us, okay, we're taking the partial in the direction of u. Okay. That's what that d sub u means. Okay, so we have this nice compact notation. It's del f dot u. And this really makes it, this kind of helps us generalize to higher dimensions, right? Okay, now that we have this kind of nice compact notation, okay, well, what if we're working for a multivariable function instead of R2 to R, what about R4 to R? Okay, and so this would be four-dimensional, right? And this would be four-dimensional. But, the notation is the same and the idea is the same. Okay. So let's say we're working in just this general dimension Rn now. Okay. If u is a unit vector in Rn, and f is a multivariable function of x1 to xn. Okay. Remember, we can use that, the more variables we have, the simpler it is to just use this compact vector notation. Okay. So let's say this function is differentiable and u is a unit vector. Okay, what is the directional derivative d sub u of f of x? Well, it's going to be the same exact thing. It's going to be del f dot u, except now this is n dimensional. This is n dimension vector, and this is n dimensions. But the operation is the same. Okay, this is still the vector of my partial derivatives, and this is still my unit vector. Okay, so if let's say u is equal to, instead of a and b now, let's say our vector u is equal, it's the vector with the components u1, u2, u3, and so on up to un. And then my del f is what? Df dx1, etc. to df dxn. Well, then my directional derivative is going to be the dot product of those two. So dou f over dou x1 times u1, dou f over dou x2 u2, plus, and I continue on all the way up to dou f over dou xn times un. Okay, so it's a really, when I use this vector notation, it's a really simple, clean extension to higher dimensions, right? So let's see an example. Let's say fxy, f of xyz is equal to this. What is this? This is a z, not 2. Okay, so z. Zx squared plus yz plus ln of x times sine of y. Okay, so let's find the directional derivative d sub u of f of x for this unit vector u. Okay. All right, so first I know that my notation, in writing it, my notation, my vector notation, this partial derivative is going to be given by del u dot u, excuse me, del f dot u. Okay. Well, I know what my u is. This is my u. What's my del f? I need to find my partial derivatives, right, to get my vector. Okay, so f sub x is equal to what? 2zx plus 1 over x sine of y. F sub y, what is that? Well, that would be z plus ln of x cosine y. And what's f sub z? That would be x squared plus y. That's it. Okay. So I know my partial derivatives. That means my del f, my gradient of f, is equal to this vector, 2zx plus 1 over x sine y. Z plus ln of x cosine y, x squared plus y. Okay, so that's my del f. And then the last step would just be to take the dot product of del f and u. Okay, so take the dot product of this with this. Okay, and so we could do that. It's a little bit tedious, multiplying all this out. I just multiply each of these components by 1 over square root of 3 and add them together. So I'll skip that last step, but you guys can do that on your own if you like. And again, maybe we'd be asked, okay, what is the directional derivative at some specific point, 1, 0, 1, for instance. In that case, I just plug 1, 0, 1 in for my x, y, and z, respectively, in this. Uh, one thing we're commonly interested in is how quickly our function is increasing or decreasing in a certain direction. And in particular, what direction does it increase or decrease the most in? Okay. So in which direction is the greatest rate of change? So again, thinking for the specific case, R2 to R, just because it's easy to graph, uh, it's got a good balance of being somewhat easy to graph and then kind of making you think in multiple dimensions. If yeah, okay. Um, so again, we can think of this graph of from R2 to R. We can think of it as a mountain, right? In this particular case, it kind of looks like a mountain, right? So we might be asking ourselves, okay, if I'm at this point here, so I'm at the point A, B in my domain, and then I kind of take my function, my f of A, B, and that puts me here on my graph. I'm trying to draw a straight line and can't. I'm not gonna break out a ruler. Okay, how about there? Okay, so I'm at this point A, B in my domain, and I trace it up here to find. I look at my f of A, B, and I'm kind of asking myself, okay, if I'm looking at different directions in my domain, okay, so I could like plug in different values along which of these lines is the increase going to be greatest. So it's like if I'm thinking of this graph as like a mountain, it's like, okay, in which direction is the mountain steepest? So maybe I don't want to, maybe I do, maybe I want to climb up that way. Or another way to think about it is like, okay, if I have a tangent line that kind of goes in the steepest direction of my mountain, right? Okay, let's say this is the steepest direction of the mountain, then that means this way, the opposite way, is the straightest downhill, right? So maybe if I'm going down the mountain, that's the direction I want to be going down, right? So a little argument about why we might want to find that. Okay. So I'm looking for the direction in my kind of inputs that will give me the steepest tangent line. Okay. And let's say, again, we're at that, and here I've kind of redrawn this. Uh, let's say we're at this point A in our domain, and once again, I'm looking for the steepest tangent line, or the direction uh, that will give me the steepest tangent line. Okay. Well, it turns out that that direction will be the gradient of f at this point. Okay. So what does that mean? I'm at this point A in my domain, right? I can plug, I have my gradient of f, which is all my partial derivatives. If I plug A into that, that gives me a specific vector pointing in a specific direction, right? Starting at A and maybe pointing over here. Well, it turns out that that direction will be the direction with the greatest increase. So this would be like the steepest direction, the steepest tangent line at that point. Okay. Now that might be intuitive. I think the first time I saw this, there wasn't anything particularly clear about that, but there is a nice little mathematical proof that's really, really approachable with just the tools we've learned for vectors like dot product. Okay, so that begins here. All right, so I want to find the direction of greatest increase, the steepest tangent line. Okay. So in other words, I kind of want to maximize the magnitude of this derivative, right? I want to make this number, the magnitude of this number, as big as possible. Okay. So let's consider let's consider the derivatives in an arbitrary direction u. Okay, so for right now, u can be any direction. Okay, let's think about that that uh, directional derivative. All right. Well, we know from our theorem, if f is differentiable, that directional derivative is going to be given by this del f at a dot u, okay, where u is our kind of arbitrary direction. And remember, u is going to be a unit vector, right? Okay. So now let's consider the magnitude of this thing. And this is going to give us just a number, right? So when I say magnitude, I'm talking about like the size of that number. So let's consider its absolute value. Okay. So we don't care if it's positive or negative. We just care about the kind of raw size of the number. So let's consider the absolute value. So I consider the absolute value of this derivative. And well, that's going to be the absolute value of this dot product. Now, this is a major theorem. It's called the Cauchy-Schwarz inequality. That's the inequality here between these two lines. This right side up top, and then this side, or this thing on the bottom. Okay, Cauchy-Schwarz. I forget if I don't think there's a T in Schwarz. Okay. And I believe it was introduced in section 12.2 or 12.3 when we introduced the dot product, but if not, okay. This is just a fundamental result of mathematics. It's true. Okay. So we have this inequality. So if you haven't seen that before, just take my word for it that we can go from this step to this step. Okay. And then everything else should be fairly straightforward. Okay. So we have what the magnitude, the size of this vector. Now this is a vector, right? Now we're considering the magnitude of this vector times the magnitude of this vector. Okay. So magnitude of that vector times the magnitude of that vector. Well, this u is a unit vector, so that magnitude is 1. Okay. All right. So really what we have, okay, this directional derivative in the direction u is going to be less than or equal to this times this, which is just the same as less than or equal to this. Okay. So let's interpret these two sides of our inequality. This is the amount of change in the direction u, right? This is the magnitude of our change in the direction u, and we're saying it's less than or equal to the magnitude of the vector del f at a. Okay. So whatever our change, whatever our we're talking about an arbitrary vector u now. Whatever our directional derivative is, its size has to be less than or equal to the size of this vector. On the other hand, let's consider the specific directional derivative in the direction of that gradient, right? When I plug a into my when I plug a into my del f, that's a vector. And then, okay, its magnitude might not be 1, but I can divide it by its own magnitude to make it, and then this will give me a unit vector, right? So this thing will be a unit vector. Let's, for brevity or ease, let's call this vector v. Okay, so let me kind of erase this. So let's consider the directional derivative in the direction v. All right. Well, that's going to be, oops. What is that going to be? let's just add a step here. Well, I know from my theorem, okay, this directional derivative is going to be what given by what? Del f at a dot the vector v. And then remember what the vector v is. The vector v is this thing. Okay, so now let's plug that back in for v. And we have equal signs here, right? It's not inequality. It's an equal sign here. So we have this directional derivative is equal to this thing. Okay, now let's consider the dot product. Okay, and let's consider that magnitude, right? The magnitude of that thing. Okay. Well, remember, this is just a constant, right? That's a scalar that's kind of scaling my vector del f. Okay, so this is a constant. So remember from our properties of vectors, I can pull this out of my absolute value here. Okay. So I can pull it out front here. And then my dot product becomes what? It becomes this. So del f at a dot del f at a. Okay. Well, remember when I have a vector dot itself, that just is the same. So remember for vector a dot a is what? Magnitude of a squared. Okay. So this is just magnitude of a squared. Yeah, I guess it would technically be like absolute value of the magnitude of a squared, which is just the same thing as magnitude of, a squared. Okay. So this is equal to this thing. So again, we have equal signs where we don't have any inequalities. Okay, these things are exactly equal. All right, so I have magnitude del f at a squared divided by magnitude del f at a. And so the result of that is just the magnitude of del f at a. All right, and that's the end of our theorem, but let's kind of go back and kind of recap what we did. So we showed that for any vector u, the magnitude of change in that direction u is less than or equal to this. On the other hand, in the same direction of del f at a, is exactly equal to this thing. So in any other direction, the increase has to be less than or equal to this thing. That means like this direction gives us the greatest increase. Okay. All right. So how would we see this in a problem? Let's find the direction of in which the tangent line is steepest for this function. Okay. And now we got to be specific. We'll almost always be talking about a specific point for problems like this. So let's find the direction with the steepest tangent line when we're at the point 1, 0, 1. Okay. Well, I know from what we just said that, okay, that direction is going to be del f at a, right? So we want del f of 1, 0, 1. So I need to find my del f, and then I need to plug 1, 0, 1 in for x, y, and z. So really what I need to do is I need to find my del f, right? Okay. So what's del f? Well, partial derivative with respect to x, that's what? 2xy plus 3zx squared. Okay. Partial derivative with respect to y is x squared plus cosine of z. Then finally, with respect to z, it's what? X cubed minus sine z of y. Okay. So that's my del f. And then I plug 1, 0, 1 into that. Okay, so this first term will be sine of 0 plus 3 1 plus cosine of 1, and then 1 minus 0, so 1. So my direction of greatest increase would be this. 3 comma 1 plus cosine of 1 comma 1. All right, that about wraps up 14.6. Let's see, 14.6. They talk about tangent planes to level surfaces. You can take a look at that if you like. It shouldn't come up in WebAssign. It's not to say it's not important or anything, but you can take a look at that. And then there's a little section on the significance of the gradient vector, which I don't think they're saying anything revolutionary there, but again, you can take a look at that for a little bit more intuition. But that'll wrap up the official lecture for 14.6.